All right, hello everybody. So this is the beginning of module 4 here, but we're going to sort of take a little step backwards here and go back to look at what we did in assignment 1. In assignment 1, you had to implement an ordered array class. And depending on how you sort of implemented that, like your operations could have had different runtimes. We weren't thinking about runtime when we built it, but the most straightforward way to implement like the sort of main operations on that class would probably look like this, right? So you like your insert function probably maybe runs in like O of n time there. Because the easiest way to sort of do that is to like first do a loop to figure out where the new element goes. You're like, oh, insert here, right? And then you do another loop to shift all of the following elements up by one spot there. So you have an O of n loop plus another O of n loop there like that. Same thing goes for like remove, right? The easiest way to like implement remove is you figure out with a loop where's the element, and then you do another loop that shifts the following elements down to fill in the empty spot there like that. So remove is probably running in O of n time as well there like that. And finally, of course, like exists or like any sort of thing that just determines whether or not a value exists is just like a loop to look for the element, and then you're like, oh, it's here, and you return true. Or if you get all the way to the end and you don't see it, then you return false, like that right there. One sort of caveat, right? Remember that the remove operation, you don't give it an index. You give it the value that you're wanting to remove there. If you give it the index, then we could skip this sort of first loop here, and we would just like start by shifting stuff down. The runtime would be the same, but like it's a distinction between like what does the argument mean? Is the argument the value that we're wanting to remove, or is the argument the index? And we've already like found the argument there like that. So pretty much all of those like are running in like sort of O of n time there like that, right? Now, since we know that the array is ordered, and we've learned about binary search, we could use that in these operations. So, like in insert, right, you could replace the first loop of like, hey, where's the thing that where's the spot where we want to do the insert? You could replace that with a binary search. You'd have to modify it a little bit because we're not looking for a specific like element. We're looking for like a spot where the element should go. But you could still do it in a binary search like way. So the first half of this would be log of n time. But then we still need the second loop to shift everything up and make room. So that would be an O of n time there. And log of n plus O of n is just O of n. So that doesn't really change anything there. Same thing goes for it's not erase, it's remove. Like I literally just made that mistake. Remove. Sorry about that. Right? You can use a binary search to find the element that you're wanting to remove, but then the loop that shifts things down to fill in the empty spot is still going to be there. So this shifting loop is still going to be O of n, although we get a log of n from the binary search. Again, O of n plus log of n is just O of n. Like n is worse than log of n, so the log of n isn't really like sort of helping us there like that. The only one of these that's actually going to improve is exists, because exists just has the first loop of like, hey, where's the thing, right? So we're just using the binary search and then returning true or false there. So exists would improve to log of n from O of n, but the other ones would not change there like that. So the idea here is like what would we need to do to make it so that we could use binary search in all of these and actually see some kind of improvement to all of our operations here? Now the problem with like insert and remove is they on an array, right, they have to like shift things around there like that. And as we saw when we talked about like arrays versus linked lists, the same thing that makes sort of random access on arrays fast, of everything being laid out just like sort of one after another in memory, also makes inserting and erasing things slow. So for linked lists, we solve that problems by sort of relaxing the requirement that, hey, everything has to be one after another in memory. We allow the nodes to be like wherever, and we connect them by their next pointers. So if we switched our ordered array from an ordered array to an ordered linked list, like would that help? Well, it would help with the insert and erase, right? So like the second part of insert, where it's like, oh, I need to shift stuff up to make room, that would just become O of 1. And likewise, the second part of remove, where we have to shift things down to fill in the empty spot, that would go away and just become O of 1. But the first part of it, where we have to figure out where to do the insert, where to do the erase there, that is still going to be O of n. And even worse, like we can't do a binary search on a linked list in log of n time. Like binary search requires an array because we jump around in it, right? We don't just go to the next thing or the previous thing. We're sort of skipping around when we do a binary search. So a binary search on a linked list is going to run in O of n time. So it's not any better than just doing like a sort of brute force linear search there. So like switching from like an array to a linked list like improves some things but makes other things worse. So in the end, it just comes out as like a wash, right? And none of the operations actually become any sort of faster there. So we can't just switch for a linked list here, but we could use a similar idea, right? We can create a structure with like nodes and stuff here where the elements are connected not by being like one after another in memory, but by pointers that we store inside of the elements saying like, where can I go from here? So the idea, what we're going to do next is we're going to sort of trace through a binary search and see like what kind of pattern it follows and then build our data structure around that. So let's say that we've got this sequence here. So the size of the sequence is 9. If 9 elements there like that, right? And let's say that we're looking for the value. Let's see, what are we looking for? I'm not sure what we're looking for here. We'll figure it out, right? Okay, so 6 is where we're going to start. We're going to start here in the middle, and we're going to compare to that value. Let's see here. Depending on what we're looking for, we could go left or right here. So like we're not going to look for some specific thing. We're just going to consider like both those possibilities. So if I'm looking for something less than 6, I would go left. If I'm looking for something greater than 6, I would go right. If I go left, then the midpoint of like this section here, right, is 2. So that would be the thing that I would check if the value that I'm looking for is less than. On the other hand, if the thing that I'm looking for is greater than 6, I would find the midpoint of this section, which is 11 there like that. So depending on whether what I'm looking for is less than or greater than 6, I'm either going to go to 2 at index 1, or I'm going to go to 11 at index 6. And then you can kind of plot out the rest of it here and get like a full sort of map of the way that a binary search would go. This might look familiar. This is a decision tree. Right, same as we drew for when we talked about like sort of better sorting algorithms here. A decision tree is not a data structure, right? We're not storing this. It's a picture of what the algorithm might do when we run it. Now, one thing to sort of notice about this, right, is the values in the sequence actually don't matter, right? If I go here, as long as I know the size of the sequence, I can draw out the decision tree that tells me where to look. It says, you know, first we look in the midpoint, which is at index 4. So whatever value is in here is going to tell me which way to go. If it's less than, then I'm going to go to 1, and I'm going to check the value that's over here like that. So I don't actually need to know the values in here to draw the decision tree. Just the number of elements determines the structure of the decision tree here like that. So the idea is we're going to build nodes that have embedded in them pointers telling me how to search to the left and how to search to the right there like that. So that way going left, instead of being like, oh, find the midpoint in terms of indexes, we'll just follow the left pointer. Going right is just following the right pointer. The nodes, again, are not sort of arranged in any kind of like, you know, pattern in memory. They're just placed wherever we sort of find room for them. And it's the pointers that tell me how to get from one place to another. So what we're building is a particular type of a binary tree here. So like, let's fix some terminology here. So a binary tree, the definition of this, sort of, you know, mathy definition is it's composed of nodes where every node has between 0 and 2 children, and the children are also nodes there like that. A quick note that the empty tree with no nodes, that is a valid binary tree. So like a lot of our code will be like, all right, what do we do if the tree is empty like that? And then although this description just says, oh, we might have 0 or 1 or 2 children, usually if we have one child, we distinguish between like left and right there like that. Because we're going to use left for less than and right for greater than when we sort of go on to do the binary search stuff here. But right now we're just like, they're just sort of left and right and they don't have any meaning yet. With some more terminology here, so we're going to draw our trees looking like this. And the top level node, the thing at the very top like that, is always called the root. In computer science, trees grow upside down, so the root is at the top, and as we'll see in a second, the leaves are at the bottom of it there like that. The root of a binary tree is like the head of a linked list. It's where we sort of start. So from the root, we can get to all the other nodes there like that, but we may not be able to get back to the root depending on what kind of a binary tree we're building there. The size of a binary tree, which as usual we'll write that as like n, right? That's just the total number of nodes in it there. So in this case, the size would be 9. There are, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 nodes in this tree here, like that right here. The height of a binary tree is the number of nodes along the longest path from the root, so up here, right, to the bottom of the tree. So whatever the deepest most sort of node is there, you count the nodes along that path. So there's 2 paths here that have the same height. So 1, 2, 3, 4 to the bottom, or over here 1, 2, 3, 4, like that. So the height of this tree is 4. Now I'll mention here sort of like there's some alternate definitions that would say that when you count the height, you don't count the nodes, you count the connections, like the blue arrows in between them. So those would count the height as 1, 2, 3, or going this way, right? 1, 2, 3. So that would give a height of 3, like 1 less than sort of like what we've given there like that. I don't particularly like that definition because the problem then is what is the height of the empty tree? If you use this definition, the definition that I'm giving, the height of the empty tree is 0. If you use the definition of like counting the blue arrows, the links along the path there, the height of the empty tree is like undefined, or some versions use like -1, neither of which really makes like a lot of like, seems kind of nice like that. So in this one, like there's this definition for height covers all possible trees, including the empty tree. So that's why I like this one. But if you go look this up somewhere else, just like be aware that there's like 2 sort of competing definitions for the height of a binary tree. Usually they're just like 1 apart, right? Like 3 versus 4, but they differ about what's the height of the empty tree there. Any nodes that have 0 children, those are called the leaf nodes here. So those are the nodes along kind of like the bottom level of the tree. Those are the leaves of the tree there like that. So a node with no children underneath it is a leaf node there like that, right? And note that like, you know, not all the leaves are at the sort of like bottommost level, right? If we're sort of counting the distance from the root down, some of them are at 1, 2, 3, and then others are 1, 2, 3, and 4. Another way to define like the height of the tree is like the sort of what is the maximum level of any leaf node, right? If you sort of wrote down the levels of all the different leaf nodes, what's the largest number that you sort of see there for that? All the nodes that are not the root and that are not leaves, we call those internal nodes, like that. So these are the internal nodes in here. And again, like there's some definitions would say that the root is also an internal node, in which case, like, you know, the definition of internal node is just a node with at least 1 child. But here I'm saying that like the root is not an internal node there like that. So we have 3 categories of nodes. We have the root, we have internal nodes, and then we have the leaves there like that. If you sort of just zoom in on a particular node, so here we're looking at like 11, right? And you look at just its left child or its right child in this case, you have another binary tree, right? Like if you were to just zoom in and look at 14 and 15, those look like a binary tree where 14 is the root and there's just no left child there. So another way to think of binary trees is that they're a recursive data structure. A binary tree is built out of smaller binary trees. When you go left or you go right, you find another binary tree, possibly an empty one. Like if we go left from 14, we find an empty binary tree down there. If we sort of slice through the tree like horizontally, then we call those the levels of the tree. So the root is always up here at level 0, and then going down we have level 1, level 2, and level 3 there like that, right? And again, like the height of the tree is the last level plus 1. So if you say what's the sort of biggest level that the tree has, and then you add 1 to it, you get the height of the tree there like that. A useful sort of factoid to know is that at any particular level, if you're at level k, the maximum number of nodes that you could have is 2 to the kth power. So at level 0, the max number of nodes I can have is 2 to the 0, which is 1, right? There can only be 1 node at the root. But then below it, it has 2 children, so there could be 2 to the 1, 2 nodes below it. And then below that, there could be 2 squared, 4 nodes. And then below that, if I had all of the nodes down here, like that, I could have a maximum of 2 cubed 8 nodes at the bottom there, like that right there. So that just sort of tells us like what's the maximum size of a particular level. And if you added all those up, you could get the maximum size of the entire tree for a given height there, like that. We'll do that later. If we zoom in on a particular node here, you can sort of describe its relationships to the nodes around it using some terminology here. So here we've zoomed in on the node 11, and I'm just kind of like only drawing the part of the tree that is around 11 there. So the nodes directly beneath it, we call those its children. So 11 in this case has 2 children, 9 and 14. 9 is its left child, and 14 is its right child. If you go like for all the nodes beneath it, not just directly, those are its descendants. So if you looked at all this stuff here, that would be its descendants. Or if you want, you can sort of look at its like left descendants and its right descendants. So here, this sort of dashed thing here is showing the right descendants of 11 there, like that. So it has 2 right descendants like that. And note that like the left descendants and the right descendants again are like more binary trees. They sort of like are sub trees of the larger tree there, like that. If we go in the opposite direction and we go up from 11, then the node directly above it is its parent node there, like that. So 11's parent is 6. And then finally, if there was more stuff above 6, if 6 wasn't the root, right, all that stuff above 11, all the way up from that to the root, those are called its ancestors. 11 only has one ancestor, and that's its parent 6. But if there's more stuff above 6 and you sort of continued along a path up to the root, you would get all of 11's ancestors there, like that. So we have, children left and right. We have parent. Sometimes we'll have like a grandparent, right, that's sort of 2 levels up there, like that. Sometimes we'll talk about siblings. So for example, 9 and 14 are siblings, right? They're sort of left and right, like adjacent to each other there, like that. Usually we don't get more involved than that. You could do weird stuff and talk about like aunts and uncles, but we don't sort of need that for anything really. There are a few different sort of classifications of binary tree shapes that will be kind of important. So a big one is balanced binary trees here. So a balanced binary tree is one where the height is approximately the log base 2 of the number of nodes there, like that. A lot of our algorithms are going to work by basically starting at the root and then kind of going down. So that means their runtime will be O of H. But if H is approximately log base 2 in a balanced tree, that means their runtime will be log of n, which is sort of nice here. So for this tree, our size is 11 and our height is 5. For a tree of size 11, if you do like the log base 2, right, of 11, you get something between 3 and 4, like that. So you can't have a fractional height, so if you round that up, you'd expect it to have a height of around 4. So the height for this one is only like 1 greater than what you would sort of expect from an ideal sort of perfectly balanced tree, which a lot of times isn't even like possible there, like that. So balanced trees are kind of like, what we sort of want to have there, like that. The opposite of a balanced tree is a degenerate tree here. So a degenerate tree is one where the height is approximately equal to the number of nodes there. Like they're in the sort of ballpark of each other here. So again, most of our algorithms are going to start at the top and work their way down. So they're going to run in O of H time here. So if your tree is degenerate and H is approximately equal to the size, that means they're going to run in O of N time there, which is worse than the log of N that we sort of want to have here. So this tree has the same size as the previous one. It has 11 nodes there, like that, but its height is equal to 8. Remember that the ideal height for 11 nodes is around 4. So this one is sort of like, almost twice as tall as it needs to be here. Degenerate doesn't mean like it's just literally a straight line, right? Like we have some places where it goes in sort of splits in 2 there, like that, but it's a lot taller than it needs to be there. It's not really making use of like the right-hand side of the tree. Most of the weight of this tree is on the left-hand side there, like that. So degenerate trees are something that we will want to avoid. A more sort of like a different sort of thing here is a full binary tree. A full binary tree is one where every node has 0 or 2 children. In other words, there's no one-child nodes. So if you look at this tree over here, none of the nodes have one child. They all have either 0 children or leaves, or they're 2 children. They're like that, right? So it's sort of somewhere in between there like that right there. A full binary tree doesn't guarantee that it's like balanced, right? We could go sort of like, further off to the right-hand side there like that, but it has some useful properties there. Another one that will become important sort of later on in Module 6 actually is a complete binary tree. So a complete binary tree is one where all the horizontal levels, right, all the sort of horizontal stripes are as full as they can be. They all have sort of like as many nodes as possible, except for the bottom level. So we allow the bottom level to not have all of its node here, but we require the bottom level to fill in left to right. So if we're going to add another node to the bottom level, it has to go there. Like that has to be the next node that is sort of created in the bottom level there like that. And the nice thing about a complete binary tree is that they are automatically balanced. So if you can make your tree into a complete tree, you get balance for free, basically. But it's a pretty hard restriction, so we'll sort of see later on like what kinds of trees can be made into complete trees. In terms of like implementation, like what does this look like? This is what our node structure looks like here. Boop, 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 boop. So as usual, we have the value that we're storing, which we're going to call the key. And then we have a node pointer to our left child and a node pointer to our right child there like that. Now, there's a couple of things that we will need for certain kinds of binary trees. Sometimes we have a pointer that goes up, a parent pointer, so that we can sort of go up in the tree. Without a parent pointer, we basically have the tree equivalent of a singly linked list. We can go down, but not up. So if we add parent pointers, then we can go up. But just like with a doubly linked list, then we have sort of multiple pointers that need to be updated if we do like an insert or an erase there like that. So it adds some extra code, but it allows us to go in both directions. Another thing that we might need is to store the height of each subtree in the nodes there. So instead of storing the height globally as like, hey, this is the height of the whole tree, we store in each node the height of that particular node's sort of subtree there. Again, these are things that we'll need later. For right now, the core of a binary search tree is the key and the left and the right. Of course, the key doesn't have to be an int, right? You could make a binary tree out of strings or a binary tree out of floats or whatever they're like that, but we're doing it as ints just for simplicity's sake there. Oh, this is mentioning like the parent pointer, right? So parent pointer is sometimes useful, lets us go up in a tree and not just down. And then the height of each subtree. We're going to use that when we talk about AVL trees, which are trees that like sort of balance themselves, but we won't have them for right now. So right now we'll just assume that this stuff is sort of not in there like that. So most of our algorithms on binary trees are going to be recursive because we need to go left and right. Like we're not sure which way to go. So we're going to have to do to recursively sort of explore the left and right subtrees sort of at the same time. Like in terms of what the computer's doing, it's not literally at the same time, right? But you can think of it that way sort of mentally, right? So for example, let's consider an algorithm for finding the size, the number of nodes in a binary tree. So this is going to be a function that takes a node pointer to the root and then returns an int for the size there. So the base case for these recursive functions is usually the empty tree. Sometimes it's like a leaf node, a tree of size 1, but usually it's like the empty tree. So what's the size of the empty tree? The size of the empty tree is 0. So we'll have a base case that'll basically be like, okay, if the root is null pointer, that's how we represent the empty tree, right? We're just going to return 0. So that'll be like our sort of base case in this function here. Then what about the recursive case here? So in the recursive case here, we get to use the recursive leap of faith. So the idea of the recursive leap of faith is if you can make the problem smaller, then magical recursion fairies can solve that problem for you and will give you the correct answer. So the idea here is we have a tree n which is not null pointer. So we know what the size of its left and right subtrees are. Like when I call the size function, the function that I'm writing on the left subtree or on the right subtree, those are guaranteed to give me the correct answer. They will tell me, oh, there's this much stuff in the left subtree, or there's this much stuff in the right subtree there. Magical recursion fairies will sort of make those versions of the function work correctly. So the only problem we have to figure out is, all right, if I know that this is going to give me the correct answer and this is going to give me the correct answer, how do I combine those to get the size of the whole thing? So if we know the sizes of the left and right subtrees, what's the size of the entire tree? Well, it's just the size of the left subtree, like however much stuff is over here, plus the size of the right subtree, however much stuff is over here, plus 1 for the node at the top there, like that. That's the total size of the whole thing, is just however much stuff is on the left, plus however much stuff is on the right, plus the 1 for the node at the top itself there. So the implementation is just this, right? We've got our base case right here, which we sort of mentioned. Why is this return true? I don't know. That doesn't make any sense. That should be returned 0. What is going on there? That is our base case. Okay. And then we've got our recursive case down here, which applies, again, if the tree is not a null pointer, right? If the tree is not empty. So n is not equal to null pointer, like that right there. And then that just does what we said. It says, okay, find the size of the left and the size of the right, sort of by magic, and then add 1. And then that is the size of the whole thing here. I renamed the parameter of this function n, partly to save space on the slide, but also partly because n is not necessarily the root of the entire tree, because the recursion is going to move n down into the left and down into the right parts of the tree there, like that. So just like, sort of like to sort of generalize this, right? Again, the base case is usually going to be the empty tree. So you'll say, what do I do for the empty tree? Every once in a while, it'll be like, okay, what do I do for a leaf node there? And then the recursive case is usually non-empty trees, but in it you get to sort of assume that the function that you are writing will work correctly when you run it on n arrow left and n arrow right there. So you can kind of consider those as like, oh, I already have the answer for the left and the right, and you just like, how do I combine those into the answer for the whole thing here? So when we're writing the recursive case here, these are the resources that we have, the key of the node, and then we have the function that we're writing applied to the left. Like, we know that that will work correctly. Magical recursion fairies will make it work. And then the function applied to the right there, like that. So the problem of the recursive case is just how do we combine these things here? How do we sort of take these and put them together into whatever it is that the function is supposed to do? So let's do another one, right? Like, let's do a function that gets the height of a binary tree here. So again, base case is the empty tree. What's the height of the empty tree? It is 0. Again, some versions of this would state that the height of the empty tree is undefined, or maybe that it's like -1 or something like that. In our version, the height of the empty tree is 0. In the recursive case, what do we have? Like, what do we have available to us to use? We have the key of the node, but the height doesn't depend on the keys, so like, that's not really sort of something we need. We already know, right, the height of the left subtree. Like, we can get that sort of like by magic. And likewise, the height of the right subtree. Like, that's just sort of given to us there. So assuming that this picture is kind of like drawn to scale, right, and I've got like a short left subtree and a taller right subtree, what is the height of the whole tree? Well, it's going to be the larger of the two subtrees, which in this case, if I drew this, that would be n arrow right. So the larger the max of the height of the left and the height of the right, and then plus 1 for the node there at the top there, like that. I'm using the standard library max function. You'd have to hashtag include algorithm if you wanted to sort of really use it there like that. But basically, like, this is our recursive case here. The height of a tree is the larger of the heights of its left and right subtrees plus 1. So again, like, this is our implementation here. Base case here, the tree is empty. That has a height of 0. Recursive case here, the tree is non-empty, then we recursively find the height of the left subtree, the height of the right subtree, take the larger of those two things, and then add 1 to it there like that. Any function that is going to need to like explore the entire tree is going to have to be non-linearly recursive. These two functions are non-linearly recursive, right? They go into the left and the right subtrees. They have two recursive calls inside them there. So any function that is like needs to explore the entire tree is going to have to be non-linearly recursive. Only if we have some kind of like thing that tells us when to go left versus when to go right, so that we never have to go like both at one time, will we be able to write like a linearly recursive function or a loop there like that. Anything where it's like, oh, I don't know where it is, where the information is in the entire tree, that's going to be something that's going to be non-linearly recursive. Okay, so those were binary trees where we didn't have any sort of like rule for like what keys go where. But the thing we really want to build is binary search trees here. So a binary search tree is that decision tree that we drew for binary search encoded into the pointers of the nodes here. So that the left-right pointers correspond to searching left less than or right greater than. So the sort of formal definition of a binary search tree, a BST, is this. A binary search tree is a binary tree with the search order property. And the search order property says that if you look at any node in the tree here, call it n, right, then all of n's left descendants, everything that you get to by going left from n, those are all less than n. Their keys are less than n. And all of the right descendants are all greater than n. So down here you find things less than n, down here you find things greater than n. This definition does not allow duplicate keys. It's not hard to add like the ability to have duplicates to binary search trees, but like just to keep things simple, we won't worry about it. Like maybe I'll mention it towards the end about how you would do that. But for right now, we're just assuming that binary search trees are duplicate free. So if you want to draw it out, it looks something like this, right? We have a node whose key is x. Then down here to the left, you find only values that are less than x. And then down here to the right, you find only values that are greater than x there. So what that does is that gives us a strategy for finding nodes with particular keys. If the current node is a null pointer, then stop, like, whatever we're looking for doesn't exist. So it's like, hey, find me the number 12 in an empty tree. The answer is, well, it's not here because nothing is here. So that's like does not exist as if we hit a null pointer. If the key of the current node is equal to the value you're looking for, then we stop, right? If I say, hey, where's 12? And then I give you a node that has a 12 in it, you're like, oh, it's right here. So then the node that we're looking at is the node that we're looking for. If the value we're looking for is less than the node's key, we go left. And if it's greater than, we go right? If I'm looking for 12 and I look at a node that has a 17 in it, then 12 is less than 17, so I need to go left. I need to look into its left subtree there. The tree that we built earlier is in fact a valid binary search tree because I built it by doing binary search on a sorted sequence. So if you sort of draw the decision tree for doing a binary search, you always get a valid binary search tree. The other thing to notice is that the search order property holds everywhere. It's not just at the root that you're like, oh, stuff is left is less than and right is greater than. When you look at like 2, right? If you look to the left of 2, you find only things less than 2. When you look right of 2, you find only things greater than 2. So you can look at any node. To the left, you'll find things less than. To the right, you will find things greater than there. So let's say we want to find the node whose key is 5, right? So we start at 6, and we say, how does 5 compare to 6? 5 is less than 6, right? So we're going to go to the left. So now we're here at 2. How does 5 compare to 2, right? 5 is greater than 2, so we're going to go right. Now we're down here at 3. 5 is greater than 3, so we're going to go right again. Here we are, 5 is equal to 5, so that means we're done. We found the node that we were looking for there like that. So we're just starting at the top and kind of like weaving our way down into the tree until we find what we're looking for. Now, what if we look for something that doesn't exist? Like, for example, there's no 10 in this tree. Let's say we'll look for 10 here. So again, we're going to start at the root, and we'll say, oh, 10 is greater than 6, so I'm going to go to the right. Now I'm at 11. 10 is less than 11, so I'm going to go to the left. Now I'm at 9. 10 is greater than 9, so I'm going to go to the right. And then that drops me into the null pointer that is 9's right child. So all of these nodes here that don't have anything below them, they have null pointers on their left and right hand side. I don't want to draw all the null pointers in, right? But that's what's sort of down there underneath them there like that. So if we hit a null pointer, that means the thing that you're looking for does not exist, right? If it sort of existed, it would be somewhere down here, but there's nothing down here. The other thing to notice is, let's say we wanted to add 10 to this tree. Where should it go? It should go right here. It should go where the search left off. If I wanted to add a 10 node, that would be where it would need to go. So our insert algorithm is basically just going to be the same as like our algorithm for finding things, with some extra steps at the end there like that. So the key sort of like binary search tree operations that we're going to look at are find, which returns the node pointer of the node whose key is X, or a null pointer if that doesn't exist. Insert adds X to the tree, as long as it doesn't already exist. If it does exist, then we don't change the tree because we don't allow duplicates. And then finally remove, which removes X from the tree if it exists. If it doesn't exist, then like sort of nothing happens there. We've already seen a couple of other operations, right? We've seen like size and height, and then maybe we'll take a look at the min and max functions of finding the smallest and largest trees in the keys in the tree there like that. But the key ones are find, insert, and remove there. So we'll dedicate a video to looking at those there. Okay, to just sort of sum it all up, right? So binary search trees are binary trees with this search order property that sort of tells us where keys should go. If you look at any particular node, n, all of n's left descendants are less than n, and all of its right descendants are greater than n. So that gives us a strategy for building binary search trees and then also searching in them, so that we don't have to search the entire tree to find a particular key here. The runtime, because we're starting at the top, right, and we're working our way down, is going to be O of h, based on the height of the tree there. So depending on whether we're sort of balanced or degenerated, that will be between log of n and O of n. But we'll talk about all of that in the next video, where we go over the binary search tree operations. But that'll do it for right now. Thanks a lot, everybody, for your time.